Welcome to our latest video on the topic of variable oxidation states of transition metal D-block elements. This video is suitable for A-level students. By the end of this video lesson, you should be able to recall how to work out the oxidation numbers of transition metal elements when combined in compounds and ions. You should also understand that a key chemical property of transition metals is their ability to exhibit variable oxidation states and be able to explain the reasons for this. And finally, you should be able to list the stable oxidation states that exist for chromium, manganese, iron, cobalt and copper. Now, in our last video lesson, we looked at the physical properties of transition metals, and we said that transition metals exhibit typical physical properties of metals. For example, they are good conductors of electricity, they're good conductors of heat, they have high melting points, they can be hammered or bent into shapes easily, which in other words means they're malleable, and they're ductile. Now, the reason transition metals have these properties is all down to their bonding. Now, the bonding that exists in transition metals is metallic bonding, and this is where you have positive metal ions surrounded by a sea of electrons, and the attraction between the positive metal ions and the electrons is the metallic bond. Now, transition metals differ from the metals of groups 1 and 2 as they're harder and stronger, they have much higher melting and boiling points, and they have much higher densities. And the reason for this is because the metallic bonding in transition metals is a lot stronger than the metallic bonding in groups 1 and 2. Now, the stronger metallic bonding in transition metals comes down to the greater charge on the metal ions, the more delocalized electrons, and the stronger attraction between these delocalized electrons and the positive metal ions. Now, in the transition metals that we study at A-level, the delocalized electrons are made up of 4s and 3d electrons. Now, the greater number of delocalized electrons that exist in transition metals means that the metallic bonds are a lot stronger. And I always think of the delocalized electrons as being the glue that holds the metal together. Now, in this video and upcoming videos, we're going to look at the chemical properties of transition metals. Now, transition metals exhibit the following chemical properties or characteristics. First of all, they have variable oxidation states. Secondly, they have catalytic properties, whether that be the elements or the compounds. They form complex ions, and they form coloured compounds. Now, in this video, we're going to focus our attention on the ability of these elements to exhibit variable oxidation states, and in later videos, we'll be focusing in detail on each of these other chemical properties. Now, before we go through the reasons why transition metals have variable oxidation states, it's important that we first recap the meaning of the term oxidation state or oxidation number, and then recap the rules for assigning oxidation numbers. Now, if you feel confident that you understand the meaning of the term oxidation number or oxidation state, and that you understand the rules for assigning oxidation numbers, you can fast forward this next section of the video. Now, in our previous video on the topic of oxidation numbers, we learnt that the ratio of elements in a compound depends on the combining power of those elements. Now, a method of expressing the combining power of elements when forming compounds is to use the term oxidation number. Now, the oxidation number is the number of electrons that need to be added or taken away from an element to make it neutral. So, for example, if we have the compound calcium chloride, CaCl2, this is made up of Ca2 plus ions, calcium ions. It's also made up of Cl minus ions, chloride ions. And this Ca2 plus ion in calcium chloride needs 2 electrons to make it a neutral calcium atom. Therefore, we say that the oxidation number of calcium in this compound would be +2. Now, the oxidation number has the same value as the charge of the ion. However, when we write the oxidation number, we write the positive charge before the number when we're writing oxidation numbers. So it's +2 instead of 2+. Now, the +2 means that we just need to add 2 electrons to this calcium 2+ ion to make the neutral atom. Now, if we look at another example, so I'm going to look at the aluminium ion, which is Al3+. The oxidation number for aluminium is +3 because an Al3+ ion needs to gain 3 electrons to form the neutral aluminium atom. Now, once again, when writing the oxidation number, the value of the oxidation number is the same as the charge, except that we write the positive charge first. So instead of it being Al3+, the oxidation number for the Al3+ ion is +3. I put the positive charge first. Now, when working out oxidation numbers, there are a number of rules that we have to consider. So let's look at these rules in turn. So the first rule that you have to remember is that the oxidation number of an uncombined element is 0. So for example, aluminium metal, copper metal, oxygen gas, they're all elements and they have oxidation numbers of 0. Now, group 1 metals such as sodium and potassium have an oxidation number of +1, while group 2 metals such as magnesium and calcium have an oxidation number of +2. Now, this should be no real surprise because you should be familiar with the fact that sodium ions are Na+, potassium ions are K+, magnesium ions are Mg2+, and calcium ions are Ca2+. And we've already just seen that the oxidation number is the same value as the charge, except that we have to remember to put the sign before the number when writing oxidation numbers. So for example, if we have a sodium ion, Na+, the oxidation number is +1. If we have a magnesium ion, Mg2+, the oxidation number is +2. Now, the next rule that we have to remember is that the oxidation number of oxygen in compounds is usually -2. You should be familiar with the O2- ion. Now, the exception to this is with peroxides and when the oxygen is bonded to fluorine. So, for example, in hydrogen peroxide, H2O2, oxygen has an oxidation number of -1, while in F2O, oxygen has another unusual oxidation number of +2. Now, these are exceptions to the rule because in the majority of cases, oxygen has a -2 oxidation state when in a compound. Another rule you should be familiar with is that the oxidation number of hydrogen is +1 in a compound. Now, the only exception to this is with metal hydrides such as sodium hydride, where hydrogen has an oxidation number of -1. Now, the next rule you should be familiar with is that the sum of the oxidation numbers in a compound is equal to 0. For example, if we take the compound aluminium oxide, Al2O3, aluminium has an oxidation number of +3 here, and oxygen in the form of the oxide ion has an oxidation number of -2. So the 2 aluminiums have a total oxidation number of +6, while the 3 oxide ions have a total oxidation number of -6. The +6 from the aluminiums and the -6 from the oxygens cancel out, and therefore we have a combined oxidation number of 0. Now in all compounds, the sum of the oxidation numbers will be 0. Now the last two rules you need to be familiar with when assigning oxidation numbers are as follows. In an iron, the sum of the oxidation numbers equal the overall charge. So for example, in the sulfate ion, which is SO4 2-, the sum of the oxidation numbers are equal to -2 because the charge of the ion is 2-. So this is because 4 oxygens have a total oxidation number of -8, 4 times -2, and sulfur has an oxidation number of +6 in this ion. So therefore the sum of the oxidation numbers +6 plus -8 equals -2, the charge on the ion. Now the last rule you have to remember is that in chemical compounds and ions, the most electronegative atom is assigned the negative oxidation number. So for example, in F2O, fluorine is more electronegative than oxygen, and therefore it's fluorine that has a -1 oxidation number here. So with 2 fluorine atoms here, it has a total of -2 for its oxidation number. So therefore the oxygen in F2O must have the unusual oxidation number of +2. So before we go through the different oxidation numbers that transition metals can exhibit and the reasons for this, let's test your understanding of this concept with some practice questions. Read through the practice questions, pause the video, have a go at them, and then we'll go for the answers. Now this practice question is asking you to work out the oxidation number of different transition metals in a series of transition metal compounds. Now the first question is asking you to work out the oxidation number of manganese in MnCl2. So we know that Cl is a -1 oxidation number. So I've got 2 Cl, so that's a total of -2. So the oxidation number for manganese must be +2. Now remember, in a compound, the sum of the oxidation numbers must be equal to 0. Now in the next example, we have vanadium in V2O5. So oxygen is -2 oxidation number. There's 5 oxygens, so it's -10 total oxidation number. So V2 must have a total oxidation number of +10, so each vanadium must be +5. Now question C is asking you for the oxidation number of chromium in Cr2O7 2-. So oxygen is -2. There are 7 oxygens, so that's a total of -14. The iron has a 2- charge, so we have to cancel all the minuses but 2. So therefore the 2 chromiums have a total oxidation number of +12, and each chromium therefore has an oxidation number of +6. Now you might recognize that the Cr2O7 2- ion is the dichromate ion. Now in D we have to find the oxidation number of copper in CuCl4 2-. Cl has a -1 oxidation state. There are 4 Cls here, so that's -4. The overall charge on the ion is 2-, so therefore the charge on the copper must be +2, because remember we have to cancel out all the minuses apart from 2 because the charge on the ion is 2-. So the oxidation number of copper here is +2. There's 1 mark for each correct answer. So the next thing we're going to look at is the variable oxidation states that can exist in the first row of the transition metals. Now one of the key features of transition metals is this ability to exhibit a range of oxidation states or oxidation numbers. And the following table shows the possible oxidation states of the first row of transition metals, with the most common stable oxidation states shown in red. Now we're not expecting you to memorize this table. However, you are expected to know the stable oxidation states of the elements that I've highlighted here. So chromium, manganese, iron, cobalt and copper. So for example, chromium can exhibit a range of oxidation numbers. However, the most stable oxidation states are +3 and +6. You are expected to know this for the exam if you're studying the WJC syllabus. Now for manganese, manganese can have +2, +3, +4, +6, +7 as stable oxidation states. It can exhibit other oxidation states, but they are not that stable. Now iron can have a range of oxidation states. However, its stable oxidation states are +2 and +3. Now for cobalt, again, a range of oxidation states can exist. However, the +2 and the +3 are the only stable oxidation states. Now for copper, both +1 and +2 are stable oxidation states. However, the +2 state is the most stable. Now, although we're not expecting you to learn this table of oxidation numbers, it is useful to understand the trends and patterns that occur within this first row of transition metal elements, sometimes called a series. Now, the first trend is that the most variation in terms of oxidation states occur in the middle of this transition series. For example, manganese has the most possible oxidation states. Now, a second trend is that the highest oxidation numbers observed also occur in the middle of this transition series. Manganese has the highest oxidation number observed, +7. Now, for many elements, the maximum oxidation number observed corresponds to the element losing all its 4s and 3d electrons. Now, for example, manganese has 5 electrons in the 3d shell, and it has 2 electrons in the 4s shell. So its electron arrangement ends in 3d5, 4s2. Its maximum oxidation number is +7 because it's able to use all these 4s and 3d electrons in its bonding when it bonds to other elements. Now another example is chromium. Chromium's electron arrangement ends in 3d5, 4s1. It therefore has 6 electrons in the 4s and 3d orbitals. Now chromium's maximum oxidation number is +6, and this corresponds to all chromium's 4s and 3d electrons being used in bonding. In other words, all 4s and 3d electrons in chromium are lost when it bonds to other elements. Another example of this is vanadium. Vanadium has an electron arrangement that ends in 3d3, 4s2. Vanadium has 5 electrons in the 4s and 3d orbitals. Its maximum oxidation number is +5, and this corresponds to losing all its 4s and 3d electrons. Now, one final trend that I'd like you to be aware of is the fact that the +2 oxidation state becomes more prevalent as we go from left to right in this transition series. So for example, on the left hand side of this series, the +2 state rarely occurs. However, as you go from left to right, the +2 oxidation state becomes more common, and when you get to zinc, it's the only oxidation state that exists. So now let's look at the reasons why transition metal elements have variable oxidation numbers. So let's start with a metal that's not a transition metal. Let's start with magnesium. Now we've seen previously that elements such as magnesium only can exhibit one oxidation number. So for example, magnesium can only have an oxidation number of +2. Now, to understand why this is the case, we must look at magnesium's successive ionization energies. Now, ionization energy is the minimum amount of energy required to remove an electron in its ground state from a gaseous atom. And here we've plotted ionization energy against the number of electrons removed for magnesium. Now, magnesium has an electron configuration of 1s2, 2s2, 2p6, 3s2. Now, it's an s block element because the last two electrons that are being filled in orbitals are being filled in s orbitals. Now, if you look at this graph closely, you'll notice that after the first two least strongly held electrons are removed, the 3s electrons, there is a big jump in ionization energy as the next 8 electrons are in a new shell, shell 2, which is closer to the positive nucleus. That's why they're harder to remove and they need more energy. Now, for this reason, magnesium only tends to form Mg2+ ions and have an oxidation state of +2. Now, energy is required to remove electrons. However, energy is given out when bonds are formed. Now, because magnesium has 2 electrons in its outer shell, and these are the least strongly held electrons, and once you remove them, the next electrons are being removed from a shell much closer to the nucleus, which require a lot more energy to remove them. This is why magnesium will only form a 2+ ion and have a +2 oxidation state. There is not enough energy to compensate for removing this extra electron by forming an extra bond. So magnesium can't be a +3 oxidation state because there's not enough energy given out by forming an extra bond to compensate for this big jump in ionization energy. Now, transition metals can exhibit variable oxidation states, so they can have multiple oxidation states, unlike elements such as magnesium. Now, the reason for this is that multiple electrons can be removed without big jumps in ionization energy. Now, the reason that there are no big jumps in ionization energy comes down to the fact that the 4s and 3d orbitals are similar in energy. They're a similar distance from the nucleus. So when a transition metal bonds to another element, it's losing the 4s and the 3d electrons. And as these are similar in energy, there are no big jumps in ionization energies when you remove these electrons. The ionization energy just increases steadily. Now, ionization energy will always increase when you remove an electron, because when you remove an electron, you're forming a positive ion, and then it becomes harder to remove the next electron. So because the 4s and 3d orbitals are similar in energy, there's a potential to remove all of these electrons. The transition element can use all the 4s and 3d electrons when it bonds to other elements. Now, if we look at this graph of magnesium and vanadium, successive ionization energies here, where I plotted ionization energy against the number of electrons removed, you can see that in magnesium there's a big jump after the second electron is removed, and for vanadium we don't see this big jump as we remove the 4s and 3d electrons. We do, however, see a jump after we've removed all 5 of vanadium's 4s and 3d electrons, because the next electron that would be removed would be from the 3p orbital, which is closer to the nucleus and therefore harder to remove. So we don't see any big jump while we're removing the 4s and 3d electrons, but we do see a jump after that. Now, for vanadium, the maximum oxidation number observed is +5. And that's because vanadium has 5 electrons distributed in the 4s and 3d orbitals. Its electron arrangement ends in 3d3, 4s2. Now, energy is needed to remove an electron from a transition metal, ionization energy. However, energy is given out when bonds are formed. Now, the reason these elements may only exhibit certain oxidation states when bonded to other elements is, although it only takes a small increase in ionization energy each time you remove an electron, that has to be compensated by the energy given out when bonds form. Now, you could have a scenario where a transition element doesn't use all its 4s and 3d electrons when bonding to a certain element, and this is because not enough energy is given out when forming bonds to this element to compensate for the extra ionization energy that would be needed to remove these electrons. So now let's test your understanding of what we've learned today with some practice questions. Here's the first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 1. So in question 1, you're asked to work out the oxidation number of some transition metals in some transition metal compounds and ions. So in question 1a, we have the carbonate ion here, which is CO3 2-. So we have -2 oxidation number for the carbonate bit, and the cobalt will therefore be +2 because the sum of the oxidation numbers for a compound must equal 0. So in B, we have iron in FeOH3. Now, it's an OH- ion, so we have -3 for the OH3, and therefore the oxidation number for iron must be +3, so that the sum of the oxidation numbers equals 0. Now for C, the oxygen is -2 oxidation number, so in CrO42-, we have -8 for the 4 oxygens. The iron has a 2- charge, so therefore the oxidation number of the chromium must be +6, so that when you have +6 - 8, it equals the charge on the iron. Now for D, we have nickel in NiCN42-. Now the cyanide ion is Cn-, so therefore we have 4 CNs, so we have a -4 oxidation number. The charge on the iron is 2-, so we have to cancel all the minuses but 2, so therefore the oxidation number of nickel is +2. Now this question is worth 4 marks in total, with 1 mark for each correct oxidation number. So now have a go at our second practice question. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 2, you're asked to give the full electron configuration of iron and an iron 3 cation, Fe3+. So for iron, the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. And you'll remember that the 4s fills before the 3d, and this is because it's slightly lower in energy. Now for an iron 3 cation, the electron arrangement is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Now this is because the first 2 electrons are removed from the 4s orbital, and the third electron to be removed is from the 3d orbital, and therefore that's why it ends in 3d5. Now we've learned previously that the 4s orbital fills before the 3d. However, when removing electrons, the 4s electrons are removed first. Now question 2a is worth 2 marks. There's 1 mark each for each correct electron configuration. Now question 2b states that iron forms both Fe2+ and Fe3+ ions. Explain why transition metal elements such as iron form compounds with more than one oxidation state. and this is a 2-mark question. So to get the marks, you need any 2 of the following points. So first of all, you could say that the 3d and 4s electrons are involved in bonding. You could also say that the 3d and 4s electrons are the electrons that are lost, because remember, when transition metals form compounds, they have ionic bonding, so they lose electrons. Now you could also say that the 3d and 4s levels are very similar in energy, or you could say that they have similar ionization energies, or different numbers of electrons can be removed. And then the other point that you could say is that energy released in bonding is sufficient to balance the energy needed to ionize each electron. And there's a maximum of 2 marks here, so you needed 2 of these points to get the marks. So to summarize here, you could say that the 4s and 3d orbitals are similar in energy, and therefore multiple electrons can be removed without big jumps in ionization energy, and the energy released in bonding has to be sufficient to balance the energy needed to ionize each electron. So it takes energy to remove these electrons, however energy is given out when you form bonds. So that concludes this video lesson. After watching this video, you should now be able to recall how to work out the oxidation numbers of transition metal elements when combined in compounds and ions. You should also understand that a chemical property of transition metals is their ability to exhibit variable oxidation states and be able to explain the reasons for this. And finally, you should be able to list the stable oxidation states that exist for chromium, manganese, iron, cobalt and copper. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.